Hi, Mika des. Hello, everyone. I am Mika, your company man, VTuber with his head in the clouds for always flying planes. We are not flying planes today. We are talking about an NTSB final report. This is kind of way different than what we usually do, but my God, I was reading through this and I was horrified at like every turn. So now I want to share that with you guys. So let's start with, I guess, a who, what, when, where, how, and why for not the event yet. We'll get into that later, but kind of why I'm doing this. So who am I? I'm Mika. That is my stage name, of course. I'm not going to give you my real name. I am a mechanical engineer. I graduated from an ABET accredited university. Unfortunately, due to the fact that I do not want to dox myself, we're gonna just we're just gonna take my credibility and we're gonna say that yes, you can take it or leave whatever I'm gonna say here. I'm not gonna blame you. We're not gonna argue about my credibility here. So if anyone's gonna be like, well, you're not credible in this, leave it, get out, done. There's room for disagreement of some of the things that I say. You know, that's how it is. But like, for me to establish credibility in this, I would either have to dox myself by handing over my university diploma, which, yeah, no way in hell, or I would have to spend like a month digging through every textbook and work I've ever done to back up what I'm talking about. But most of what I'm going to talk about is pretty elementary mechanical engineering. On that note, I am not a submersible designer. I do not know much about designing submarines. Well then, Mika, how can you talk about the poor design of a submarine? Well, that's simple. Because they made some elementary engineering mistakes in this. Like, fundamental engineering mistakes have been made. We'll go through what those are. I also do not have a lot of experience with composite materials. I have worked with I guess the majority of my materials experience is with steel, aluminum, and actually a composite, but it's not this kind of composite. That would be glass-filled nylon. Glass-filled nylon is quite drastically different from the carbon fiber composite that was used to construct the Titan. Again, I don't need to go into my credibility or I don't need to be a materials expert in carbon fiber to explain the fundamental theories of it. If you were to ask me to construct a carbon fiber anything, I would probably run into troubles with it. However, I can tell you some of the pros and cons of it and explain some of the core difficulties that carbon fiber has as a building material. And I'm realizing I forgot to grab a good example for some of this, but I've got plenty of cords laying around that I can use. We'll get into that. Why am I doing this? Well, I mean, like, since the news of this came out, I've just been horrified. And then the final report came out, and I was even more horrified. So let's start with what I have said. I don't think I've really like made a lot of public statements. I've said a lot to friends, but what I have said in the past of what I thought was the core issue, the problem, what happened with the Titan submarine before this report came out. And of course, I have read this report, as I've mentioned, but when it came out that the submarine had imploded, I immediately went to like, oh yeah, carbon fiber pressure vessel. That's a problem. That's like where I'm gonna point my finger. That is a huge problem.
Warning. Spaceman 634 gifted a tier 1 subscription to Quenterich.
And the reasoning behind that is because carbon fiber is not very good as a pressure vessel in that way. Man, maybe I should have scripted this out, or I should have bullet pointed this out more. There's a lot to cover and a lot of different places, so we might just repetition it. So we're gonna get to the first part. Well, carbon fiber isn't a very good pressure vessel and in terms of a submarine, it's great for holding in pressure. It's bad for holding out pressure. And I'll explain that in a minute. The next thing is that information had come out a while back that this wasn't the submarine's first dive, so that allows us to eliminate first cycle yielding, and I'll explain what first cycle yielding is. And then it had done a number of times. It had gone through a dive a number of times, which to me sounds like a process issue, design process issue, and failure to notice things. Because generally, if something is designed at least somewhat competently, it's not going to fail outright. It can happen if you've got the right circumstances, but I wouldn't expect that of this. Normally, materials are going to start visibly deforming. You're going to be able to catch some of it. So let's start out with I guess we could start out with carbon fiber and why it's not a good material for a submarine. Or at least not necessarily, I guess, submarine, but not good in holding pressure out. So probably should have brought a circle for this. And I'm going to hope that you guys can pick this up. I got a piece of tape here I can use as a circle. So actually, I probably should explain the construction of their submarine first. So their submarine, their hull is a circle that you guys can't even see. Okay. Let me see if I can't turn this off and then get enough exposure on here. Probably going to be a lot. Yeah, it's going to be really slow this way. Dang it. I'm going to need a marker. You're really going to make me use a marker on this? Stupid camera. We could see it like this. Okay, it's fine. All right, so the Titan submarine, it has a carbon fiber composite section in the middle. You know, it's a cylinder. Oh, and my cheap light is going to give me grief. The submarine also had a construction like this. So you have your carbon fiber section in the middle, and then at the ends, there are titanium sections. Titanium is a great material. It's lightweight, it's strong, and it is, as far as I understand, relatively isotropic. Isotropic, what does that mean? So, that the sub lasted through as many dives as it did is kind of a miracle. Kind of yes, kind of no. I'll go into that a little bit more because I'm still kind of explaining here what my reaction to this has been pre-report, and then we'll go into the post, the report itself, and be even more horrified. Okay, so the submarine was constructed 2 titanium hemispheres. One of them had a viewing dome, and then the middle primary portion of the pressure vessel is carbon fiber. Now, with this construction, assuming that the titanium end caps are relatively rigid compared to the carbon fiber, which is reasonable enough, what you'd end up with is when you're under pressure, your hull is going to draw the end caps first. Your hull is going to come down like this. It's going to get squeezed. The titanium will support it at the ends, but your pressure is coming from all over, everywhere. That's hydrostatic force. For, I don't remember, like, rho GH, it's the density of the liquid times gravitational constant 9.81 meters per second, times the height of the water column above that part. So it's, if we neglect the minor difference in water pressure, which at these depths, it is a minor difference in water pressure between the top and the bottom of the submarine, then your pressure is the same all around your submarine. So if we take a small square chunk, so let's say we take an infinitesimally small, like a super tiny chunk out of this ring, what do the forces look like? Well, we get cube, and I'm gonna have to draw a cube.
Caution.
Alex Lebrun, thank you for the follow. But we get a cube. As I draw it poorly, it's a good thing I've got an eraser. So this cube, should have picked an easier cube to work with. We'll say that it's right here at the bottom instead. So, what are the forces on the cube? Well, on this right side, the right side here, it is being pushed by the other cubes around it. This is a cylinder. A cylinder acts like an arc. You've probably seen, or an arch. You've probably seen information on an arch and how it distributes the forces and everything's just in compression in an arch, right? That's how a cylinder works. At least, theoretically, a thin-walled cylinder, which I will also add the caveat that my experience with forces in pressure vessels are only thin-walled pressure vessels, not thick-walled pressure vessels. The Titan hull is 5 inches thick. So that is not a thin-walled pressure vessel. That is very much a thick-walled pressure vessel. So there's some stuff going on in there, but I think that we can neglect it for the most part in our discussion because the forces going on just makes it work better than it theoretically would if it were a thin-walled pressure vessel. Were it a thin-walled pressure vessel, it wouldn't work at all, in theory. So, from this right side, you've got a compressive force on it. From the left side, you've got a compressive force on it. From the outside, you have a compressive force on it. There's nothing backing it up except, really, there's other layers. If we took a slice all the way through, there'd be nothing backing it up. But there's material behind it that's theoretically backing it up. That may not be that much of a force, but that's where the thick-walled pressure vessel issues comes in. I don't know that. Now, this front and back, which are oriented, our cube is here, remember. What's happening? Well, it's getting pulled apart. Okay? So, depending on how your composite's made, that might not be a problem. That might be a big problem. But carbon fiber, generally, you wind fibers along the cylinder. So you have a wrapped cylinder like this. So the other problem here is that we have a fiber. This is a fiber with a resin in it. Imagine the fiber is something like a cord. You can pull on it. It's really strong. But what happens when you push on it? There's no compressive strength at all. And in a composite like carbon fiber, the only compressive strength that you gain in it is whatever the resin provides. So your carbon fiber is really not getting you anything in that. But then we look back at our cube and we say that, okay, our cube's mostly in compression with a little bit of tension. So clearly we need a material that's good in compression. And what material did we pick? One that's really fucking bad in compression. Why? Why? God, why? Please, for the love of God, why? This has been the crux of my issue for the entire duration of the talk about this submarine. I've seen people talk about, oh, well, carbon fibers, well, it's a new material, and like 20 years ago, people were saying that about the acrylic, like the acrylic used in their window. Well, there's a difference. Acrylic is a thermopolymer. Thermopolymers, generally, and I didn't look this up, but I can make a completely reasonable assumption here because I have worked with acrylic before. Most thermopolymers are relatively isotropic. So that means that they handle forces in all directions pretty well. Well, I should probably explain what are the main forces. that a material exhibits. So if you have your piece of material here, you have pulling it apart, tension. You have pushing it together, compression. And then you have a third, which is actually both of these, and that is bending. So if you take this and you put it, a force here, and a force here, you get bending. If you have something like steel, it's good in all of these pretty much equally. Its ultimate failure strength will be the same pretty much in all of these conditions. Titanium, similar. It's going to be the same in all these conditions. A thermoplastic, like acrylic, it's actually going to be pretty similar in tension and compression, but when you put it in bending, it actually gets really good in bending. Or not really good, but it gets better in bending. Most thermoplastics that I've worked with, when you put them in bending, they actually do better than tension, which is great. So thermoplastic in this application, not really a bad idea. And you can think of particularly their porthole that's here. It's getting forces on it here, 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 here. It was shaped like a dome that's flat. And then it was supported roughly around here. I'm not going to go into much of this because basically the dome was not a problem at all. And I didn't think the dome was going to be any problem. You've got all your forces here. And you've got a nice arch. This thing is primarily in compression and bending. Acrylic is great at those. This is no problem. So when people say 20 years ago, 20 years ago, acrylic wouldn't have been seen as an acceptable material. That's different from what we're saying now about how carbon fiber is not a reasonable material for this. You can make it work. They have shown that you kind of can make it work, and we'll get into a bit more about how they could have made it work completely safely. But it is really not the material you want to pick for this. You are... God, I would say you'd probably be better off by just chopping the fiber up and using like a matting like is used on some airplanes instead of wrapping this thing. Like there's not a lot of strength to gain by wrapping it this way. And I believe they might have wrapped it transversely, which would have been going from here to here, which would help with these forces. And it would actually be really good against those forces because now you're putting an intention there. So you're taking this off, but like the rest of it, you're really not doing much. And I think the thickness of the pressure hull says quite a bit about the troubles they had in getting a tensile material to handle very well and compressive. The other thing that I've said is that, okay, their submarine survived a couple dives. Like it had been known that they had survived a couple dives to the Titanic specifically beforehand. And then it suddenly failed. Well, why is that? Well, let's talk about stress, strain, and fatigue failure next. So I need to get out my handy dandy slide rule and use it as a ruler. I'm sorry that I'm using a slide rule as literally a ruler, but this one actually has ruler graduations on it. So sorry, not sorry. So here we have a graph. And on this axis, we're going to put strain. Sorry, I can't spell while I'm talking. I'm not able to do that. And then we have stress. Well, before we start plotting anything on this, what is stress and what is strain? So strain is when you take a material, so like let's say that sample we had before, and we start pulling on it. What happens with every material, I mean, there's not been a single material we found that doesn't do this. when you take it and you start applying a force on it, it stretches. It may not seem like it, but it does. Basically, every material, like you can take a big chunk of steel and you can start pushing, pulling it, and it will start to move. That difference in length between when we started and when we between when we had it and when we started pulling, that is the strain, and it's typically a unitless or a percent. And it's just the amount that it has grown over the divided by the original length. So that's makes it a percent, because it percent or unitless, because it's millimeters over millimeters. The millimeters cancel out to unitless, the percentage. Strain is really useful because strain is what actually matters in a material. Stress is how much force we're putting on it, and it's what we care about in a material, because we don't care. We typically don't care most of the time about how, if I put a truck on this bridge, how much is the bridge going to deflect? Generally, we don't care about that because strain values are really small. The material does care about that because that's the material being deformed, and that matters. But we care about stress more because stress is a little bit easier to calculate and work with rather than like a load or a strain. So most materials have a stress strain. Well, pretty much every material that's been studied has a stress strain curve. And most of the time, they look something like this. So you have a nice linear portion, and then it will come up, and it'll go curve, and then it'll come back down. And sometimes it'll go back up again, depending on your material, but that's really fucky. So what do we have? We have a nice linear portion. This section right here, this is elastic deformation. So as you apply stress, the strain will increase, and you release stress, it'll come back down. When you're in this elastic deformation period, the material is fine, it's in its lane, it's moisturized, it's great. This is the basis of like everything. You can keep going up and down this as long as it stays along the same line. If you've got steel, it'll do this forever, as long as you stay low enough on this. There's some caveats in there, but steel will get indefinite lifespan rather, as long as you stay in the elastic region low enough for your application. Then you get up higher and you get plastic. So this is where things are permanently distorting. That's bad. Once you start getting into plastic deformation, that's the yield strength. We can highlight this out. Yield. Once a material has exceeded its yield strength, it has permanently deformed. It will never return to its original frame, its original shape. When you take load off of it, it will need to be forced back into position or remade. Now, why does that matter? Well, the second you have a part that yields, your calculations are now wrong. Unless you've accounted for yielding, which I don't know. If you are accounting for your material yielding, that's, on one hand, that's terrifying. On the other hand, it might just be good design. It's a little yikes. The problem is that it's like a paperclip. If you take a paperclip and you bend it, it'll stay where you bent it. It'll actually come back a little bit towards where it was, but it will stay permanently deformed. And then you can observe the fatigue failure of a paperclip by bending it such that it stays out of its previous position over and over again until it breaks. Now, why does this matter? Well, we also need to talk about hysteresis. So, unfortunately, most materials aren't steel. And so, what happens is they go up this elastic deformation line, and then they have the stress come off of them, and they come back down. in a different way. So they'll come up, and then they'll come back down, and they won't be at the same strain. They'll start permanently deforming. Couldn't you just theoretically cast steel into the shape of a pressure vessel and call it a day? So I have only, as I've said before, I've only worked with thin-walled pressure vessels, so I wouldn't know if casting specifically would cause problems or not. My first reaction would be no, because if you're still thin enough, you still have the box we were talking about earlier, where it's being pushed, it's being pushed, it's being pushed, it's being pushed. The iffy part would be the tensile part, which would make me want to use more of maybe like a machined or a rolled. Really, I'd rather have like a rolled plate, because a rolled, if you cast it, it's not going to be that good in tension for these bits of tension that you're getting, which, I mean, they're not bits, they're probably a significant amount of tension. If you instead machine it, machining a material causes a lot of stress to be built up in the material and causes a lot of potential stress concentration factors, micro fractures and whatnot. Forging or forming it would probably be more ideal, because you could roll it into a position. It would be a little bit hardened from the rolling process, depending on if you do it as a hot roll or a cold roll. But you'd still end up with a seam, which might be a problem. So I can't say a ton about what would be the most ideal for that, because I don't know about pressure vessel design. So that's the limit of my knowledge. I'm going to try to stay within the limits of my knowledge, and anything where I'm exceeding it, I'm going to try to make it clear. So, as I was saying, you get this hysteresis where the part goes out, you're staying within the elastic range, but it comes back down, and it's a little bit permanently deformed. This happens of basically every material other than steel, because I don't know why. Steel is fucky. I asked a professor about it. A professor said, I don't have 5 hours to give you a lecture on this, and I left it at that. I'd love to know why steel is the unique one that doesn't do this, but that's the thing for another day. But plastics plastics suffer a lot from hysteresis. It is a big problem, and it makes them a little bit difficult to work with. The other trouble with it is that sometimes they can exhibit hysteresis, and as long as the change from the geometry that caused isn't detrimental, it is really just fine. It's like, it can be really weird. Like the plastic gears that I used to work with in automotive industry, the mating between the two gears, the plastic one would deform over time, but what would end up happening is that it's just like perfectly forming itself to the other mating gear, which just makes it run better, which is great, because by the time that happened, your grease had started to exceed its lifespan. But then your parts didn't really need the grease to reduce friction or anything, and also the teeth would be able to deform to have more teeth engaged. So it's not always a bad thing in plastic, but you gotta, when it's a critical feature, you gotta know what you're doing with this. So why does all this matter? Well, because every time the Titan submarine dives, the composite hull is going to deform. It's going to get crushed like this, and it's going to come back up, and it's going to expand back, but it's not always going to go back perfectly. And that's going to cause you problems. Slowly over time, if you've got good maintenance checks, you could make this work. You just need to know what the limits of fatigue life on this shape in these conditions is going to be, so that way you can look out for it, and also so you can figure out what the signs of the failure are going to be. Because typically it's going to be a gradual failure with signs that you could identify if you know how to look for them. So you might find that, okay, we can observe it with strain gauges, And like you can slap strain gauges on things and you can directly measure this strain. It's fantastic. Strain gauges are actually pretty cheap. It's the rest of the equipment that goes with them that's expensive. But they directly measure the strain in an object. And if you can get other data to apply the stress, you can literally see real time as your parts are deforming permanently and they're not acting as you expect. That'll come up later. That's the fun part. So I've probably been all over the place with this. Does anyone have any questions on this before we get into the report? Boat go squish? Yeah. Yes, Rico, boat go squish. All right. If nothing else, let's go on to reading some of the final report. I'm going to skip over this because this is a little bit of spoilers, although you guys might have read it. So, what happened? About 372 miles off the coast of St. John's, the Titan submersible suffered a catastrophic failure pretty deep in the ocean. We're going to have to... you guys probably don't want me to read through this, so we're going to have to skip around a little bit. So here's an example of the construction that was being showed off. So we see aft segment, fore segment, and then there's a carbon fiber composite cylinder. There's my mouse pointer. So there's the carbon fiber composite cylinder. Then you have the pressure vessel here that the occupants were in. Da-da-da-da-da. They talk about the operations. I wonder what page the other thing was on. So they talk about basically the event and trying to have any response to it, which is not important for our discussion. But one of the factors in here is that the Titan had like 4 hours of air, or not 4 hours, 4 days of air rather. And it would have taken like a week to get a submersible capable of its depth to the area and operating. So that was poor planning. If something had gone wrong at depth, they did not have a chance anyway, whether or not the entire thing imploded. They talk about classification. I'm going to talk about that later when they're kind of going over the conclusions and recommendations for changes. Construction. So here's a thing. First pressure vessel design. First, that implies there's a second. Yes, it does. So before constructing a full-scale pressure vessel from the Titan, OceanGate hired Spencer Composites to complete a stress analysis for a carbon fiber cylinder design. The analysis indicated an implosion depth about 13,200 meters after the analysis was complete. They worked with Spencer Composites to construct a 1/3 scale model of the pressure vessel to visualize their prototype and test its design features. They constructed the model sometime before March 2016. Subscale model pressure vessel comprised 2 carbon fiber domes and a carbon fiber composite cylinder. The cylinder was constructed using a method called wet winding, wherein carbon fiber strands were run through a bath of liquid resin, and then the resin-laden strands were then used to construct the cylinder. So this is what I assumed they had done for a cylinder. This is not atypical of how COPVs, carbon overwrap pressure vessels for spacecraft, are made. Now, why are they done like this? Well, you get one continuous string or yarn, whatever you want to call it, that is wrapped around the thing. You're using the ability of this carbon fiber in tension to hold things in, at least in a overwrap pressure vessel, with internal pressure, not external pressure. And it's, with my limited experience, it seems like a pretty good way to do it. So the they've just got the fiber strands. They go through the resin. They get put onto the cylinder, and you just wind this continuously. This makes sense. It gives you a much more homogeneous material to do it all in one go. But then we get this quote here. According to a former OceanGate director of marine operations, the CEO chose carbon fiber because he believed it was better in compression than tension. Jesus fucking Christ. Oh my God. How do you even believe this? That is absurd. That is without base. Like, grab a string of it and try to compress it. It doesn't. Yeah, it's so backward. It is much better in tension than compression. Like, even if you take if you took like a piece of steel and you drew it into a wire, it's going to be better in tension than compression. That wire, even an isotropic material, why is it going to be better in tension than compression? Because buckling. That's what this wire is doing right now when we push it together. It buckles. If this wire was perfectly solid and we put the load on it perfectly, theoretically, it could hold quite a bit of weight, as much weight as I can pull on it. But because it's not perfectly rigid, it will buckle, and so it won't hold any load. You can't push a string. You can only pull a string. That's how physics works. Buckling is a thing that happens in real life. Buckling is really an interesting thing in engineering because, at least to my knowledge, sadly, I don't get to work too much with buckling ever outside of university. Buckling is something that buckling is something that doesn't happen in theory, which is fun because normally things only happen in theory. But buckling is yeah, it's a weird one because in a lot of our theory doesn't really do literal string physics. So you got to be really careful when it comes to buckling when you're designing certain things, particularly like bridges. And that's why usually bridges have really chunky, wide features. Additionally, since carbon fiber is lighter than other materials such as steel or titanium, the CEO believed that it would require less buoyancy and could be launched from a bigger variety of surface tenders as opposed to necessitating a purpose-built ship, and it would be easier to transport and could carry more people. So, carbon fiber is, I guess depending on your resin, it's going to be pretty light. It's typically, I believe, lighter than water, which is something you don't need in a submarine because you want it to be fairly heavy because it's going to be filled with air and it needs to be able to have neutral buoyancy typically. So I don't really see the advantage of making it lightweight other than saving cost in support equipment. And how much did they say the thing weighed? The NTSB had an estimated 4 gross tons. So it really was not that heavy of a vehicle. And this might have also been part of shenanigans that I can try to remember to mention later. During 2 successive tests of subscale models, the carbon fiber domes prematurely failed. So OceanGate replaced the carbon fiber domes with titanium end domes constructed by TIFAB. Why carbon fiber domes failing? That kind of makes sense because you're going to have just this open end that needs to be mated, and that's a big failure point. That's going to be really hard to do with carbon fiber because you've got like no ability to transfer load between these two except with compression. So how the fuck do you even do that? I don't know. I don't know how you'd make that work. You might be able to. I would not want to try it. During testing in June 2016, the updated subscale model pressure vessel imploded at a depth of 4,200 meters. According to the CEO, that model had a delamination in the carbon fiber cylinder. So delamination is, at least through what I've seen of planes and other carbon fiber things, that's kind of the failure mode of carbon fiber. carbon fiber composites like this because they're layered on. They're not really a homogeneous material. They're not the same throughout. So you end up having layers kind of like a 3D printed part that can come apart fairly easily. In 2018, Spencer Composites constructed the first V1 full-scale Titan pressure vessel with the outer hull including the fairing, landing frame, and external equipment, again using wet winding to construct the carbon fiber cylinder and titanium domes. So what we see here is there is an engineering design process. They designed it, they did scale testing to validate their designs, and that, like, okay, that's good engineering. What isn't noted here, though, is that the analysis indicated an implosion depth of about 13,200 meters. During testing, the updated subscale model pressure vessel imploded at a depth of 4,200 meters. There is some ambiguity here that I would like. It would be nice to have a little bit more information on if this analysis is only for the full scale or if the subscale one is also supposed to last that long. It is unknown. But at the very least, we know that the subscale one was tested down to a depth below what the actual submarine is supposed to go to, which gives you a little bit of a safety factor, which is important. So then, between February 2018 and June 2019, OceanGate completed 49 dives of the Titan V1 pressure vessel. They dove to various depths, so we don't have good records of, or at least this doesn't present good records of each dive. But generally, they weren't terribly deep for most. They did a few of them that were pretty darn deep. So down to 4,000 meters, you have 33 down to 4,000 meters. So that's a pretty decent number of tests. During dives 42 through 44 and 45 through 47. What? Okay, this is like poorly written. Giving me a brain aneurysm. They reported hearing cracking sounds during these dives. After dive 48, while making preparations for a dive, an employee noticed a hairline fracture in the pressure vessel cylinder and reported it. An examination of the crack indicated it originated from subsurface delamination, and they halted field testing of the Titan. Okay, so this is what I was talking about. Like, typically, confidently designed things have gradual failures. So you're going to, in a lot of materials at least, you're going to hear it, you're going to see it. As long as you carry out good inspections, you can typically identify a failure before it happens. So they shipped it back to Washington, attempted one dive, but the dive was aborted due to an issue with improperly secured blanks. That's on a supporting equipment piece. They had planned for the Titan to begin diving the Titanic wreck site 2019 and had booked clients for an expedition during that time. But the first director of engineering stated that he told the CEO because there was the crack, the pressure hole was done, and he was not going to take this Titan anywhere. And he said he wouldn't sign off on the planned 2019 expedition and was shortly terminated thereafter. So that's a big red flag. This first director of engineering, I got to give him props for standing up for this. He likely insisted on a lot of the testing. So what we saw is that this submarine was designed. It had analysis done. It had a subscale model built. Then the subscale model was tested. The full version was built and then was tested, and it wasn't quite right. The failure was identified, and it was pulled out of service, but the guy in charge of all of this was canned. So that's pretty bad. Like, hey, yeah, I'm not going to allow you to do this. All right, get fired. The V1 pressure vessel was shipped to the Deep Ocean Test Facility, then operated by Northrop Grumman in Annapolis, Maryland. Shout out to our resident Northrop Grumman employee here. And following this testing, it postponed its planned expedition. Second pressure vessel test. This is where things get really spicy. Under a new director of engineering, they embarked on a second stress analysis and testing program for a V2 Titan pressure vessel. Predicted an implosion depth of about 7,500 meters, but also indicated that the depth of the Titan was limited to 4,200 meters due to the potential for deformation of the titanium forward dome around the viewport. OceanGate constructed a 1/3 scale model to test the V2 pressure vessel. Okay, so we're seeing again that they needed to update their design, so they updated their design, and then they're making they're making a scale model to test it. Okay, that's good. That's what you're supposed to do. If you can't make a full scale model, at least. The carbon fiber was constructed using unidirectional filament wound carbon fiber pre-impregnated with an epoxy resin. So they've swapped materials now, instead of using the wet winding. So they're completely different construction method now. Then they slit the rolls to 1/2-inch wide reels and built the cylinder by winding these onto the carbon fiber, onto a mandrel. And so they're instead of winding a single fiber, they're winding a thin mat 1/2-inch wide of carbon fiber around the cylinder. What isn't brought up here is whether or not this epoxy pre-pregs mat is, well, I guess it says it's unidirectional filament. It doesn't. I'd like to know a little bit more about what other fibers are in different directions on this, because if it's all in one direction, unless it's like really woven together weirdly, I can't imagine that would necessarily be the same. But this you would expect would have a little bit more capability and tension along the length of the submarine, which is probably a good thing. I could see the need for it. They began testing the subscale model in July of 2020. The pressure vessel developed wrinkles in the carbon fiber and imploded at 2,900 meters. And they blamed the wrinkles in the cylinder as a likely cause of failure. They built a second subscale model using the same construction methods. It was tested in the same laboratory. At 2,500 meters, when the pressure vessel integrity monitoring data made it clear the model pressure vessel was going to fail, they stopped testing. So they didn't even test it to failure. They went, oh, this is going to fail, and they stopped testing. Afterwards, based on the company's experience with the subscale models and the experience of its manufacturing partners, OceanGate decided to use a co-bonding process to construct the cylinder to mitigate the development of wrinkles. Okay, so we did one test model, we did a second test model, it didn't work. So we decided that we're going to throw out that method of production, and we're not going to completely throw it out. We're going to adjust it. So they explain the co-bonding later. OceanGate constructed a second final full-scale pressure vessel using the co-bonding process. Wait, what? We swapped up production methods and we just built the final one? What? You can't do this. Like, I'm pulling my hair out. You can't. That's so horrible. You need to do testing. You need to do validation of your production method to the final product, so that you know that your calculations are on the ball. Well, let's get into how this second pressure vessel was made. So the V2 full-scale pressure vessel was manufactured from rolls of pre-preg carbon fiber, again by winding 1/2-inch wide toes onto a cylindrical carbon steel mandrel, blah, blah, blah. So they constructed it as a series of 5 co-bonded 1-inch thick composite layers. So they have 133 plies per layer, roughly. Or actually, exactly, I believe. And they did 2 cylindrical plies followed by 1 longitudinal ply. So, okay, we're also getting some extra strength along the length of the submarine, it seems. According to data published by the manufacturer, this would have resulted in just under an inch thick layer. Then they applied a removable layer, and the assembly was cured in an autoclave. Okay, so this is where I'm starting to get I don't have a dark expression for this. I wish I had. But this is where I'm starting to get sketched out on their construction method, because you've got a pressure vessel, and we're going to construct it in 5 basically separate layers of the same material. It is the same material, but you're gonna wrap one layer, then you're going to autoclave it to cure it, and then you're gonna wrap another layer. Okay, well, first things first, how are those 2 layers gonna adhere to each other? That they're completely different materials now at the point that they intersect. They're going to be autoclaved at different points of time, so they're probably not going to stick together very well. Like, even if everything is done identically, because you autoclave them at different times, they're going to have a difference in materials there. Even if it's just a difference in the stress of the material. Well, after autoclave curing, the peel ply was removed and an adhesive film was applied to the cylinder surface. So we're wrapping an 1 inch thick layer, then curing it in an basically a giant pressure oven, pulling it out, applying a glue layer, and then adding another 1 inch layer. So now not only do we have materials that are going to be cured at different times as our interface, we don't have that anymore. We have an adhesive between the 2 layers. And that's just even worse. That's a completely different material. You can make this work, but to me, that's a yikes. That's a yikes right there. Like, this is going to be a problem. And if you remember back to our cube here, the cube is a theoretical exercise. We're assuming in these calculations that this is just a chunk of a material that is the same throughout. But now we actually have 5 separate cubes in a line. And what does that do? You now have, between 2 of these, a different material, and you've got shear forces. These can move between each other. They're not the same material. Instead of deforming, they're going to shear. That's awful. Oh my god. Again, you could make it work. Personally, how do I want to state this? So, again, I'm not a carbon expert, or I'm not an expert in composite materials. So this is more of an opinion, a gut reaction opinion. But my gut says that this is fine in a pressure vessel if you've got an internal pressure pushing this out, because the layers are going to be pushed out to each other. They're going to be stretched and expanded into the next layer, which is going to be stretched and expanded to the next layer, which is stretched and expanded to the next layer, and so on through all 5 layers. When you're in compression, the outer layer is going to be pushed and compressed and shrunk down, which is going to push and compress the inner layer, and now you've got shear forces between these 2, probably of larger magnitudes than an internal pressure vessel. So I really don't like that. This strikes me as a case of, you can make it work, but you're going to have to be really careful with your selection of adhesive. You're going to have to be really careful with your process, and making sure that your process is nailed down and it's going to create a very uniform, homogeneous product. Which, spoilers. Or rather, foreshadowing. So see figure 7. So they've got an example of what we're talking about. So you apply one ply, add a peel ply, which is, I assume, just a protective thing. And then you add the second one, and you just keep repeating this. So at the end, you have 5 layers of carbon fiber with 4 layers of adhesive between it. And they actually have an actual picture of what was cut off of the hull, because this was wound and then it was cut down to size, which is kind of what you'd expect for it, this to be done. And so we have the remnants that were cut off that we can look at. And so we see that, well, first off, this is a hair over 5 inches. Actually, this looks like maybe about a 1/4 inch over 5 inches. So it's thicker than it was designed to be. That's kind of a problem. But then also, it's 5 distinct layers. That's really not good. So they say here, its cylinder was manufactured with excess material at both ends, which is subsequently trimmed off. It is then glued to commercially pure grade 3 titanium segments. There was a C channel to hold it in, and what ends up happening here is that because the C channel is exactly or is designed for a 5-inch thick cylinder, it doesn't fit. So they have to grind off. They have to grind this down so it fits. That's another alarm. Ding 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 ding. Big red flag. Big red alarm bell. You've designed this to be 5 inches thick of your carbon fiber material. When you've applied the same amount of material you designed for, it became thicker. And then you couldn't fit that in, so you had to grind it down, which is going to weaken it, depending on how they ground it down, which I think we don't know the specifics of. They could have done all sorts of damage. Particularly if there's sharp corners or a small radius, they could have introduced a stress concentration factor by cutting this down. It's really, really not good. I don't like that either. That's pretty bad. Titanium domes were attached to the segments using 18 bolts to cap the pressure vessel at each end. Okay, that's fine. Not really that bad. So what we've established here is they've got a good way. They've actually got a pretty decent way to take the load from the ends of this and transfer it to the domes as well. So that's really not a bad part of their design. The bad part is where they produced it and didn't follow the plan. The V2 full-scale pressure vessel was pressure tested at the Deep Ocean Test Facility, simulated maximum depth of 4,200 meters. According to the analysis performed under contract, depth was limited by the yield strength of the forward titanium dome at a location around the viewport. Now that I don't really like, because you can't really get a very good safety factor in this. They ended up going with maximum depth of 3840 meters. So we have 4,200 minus 3840 divided by 3840. Or sorry, that's brain is not braining today. Oh God. 3840 divided by 4,200. I did that the wrong way around. Okay, brain is really struggling. 4,200 divided by 3840. And I'm not even typing it. My God, Mika, get your shit together. Okay, so we've got a whopping safety factor of 1.09. You see a problem here? So what's a safety factor? Safety factor, as I proceeded to struggle here to calculate because I'm half brain dead still. A safety factor is typically the design or tested load divided by the intended load. So 4,200 meters of depth divided by 3,840 meters of depth, that gets you a 1.09 safety factor. Most things are designed with a safety factor. Why do we do that in engineering? Well, we do this in engineering because sometimes we admit that we do not necessarily have the whole picture for our problem. So if you understand your problem perfectly, you could build potentially with a 1-to-1 safety factor, although you really are not going to want to do that outside of like academia where you're just testing something to prove a point. Very minor things can cause your safety factor or your design loads to go out the window, and that's a big problem. And generally, we were told in university that like static objects like buildings, bridges have about a 10x safety factor, which that's a lot of safety factor, but those also have pretty unpredictable loads, although we are getting better and better every year about figuring out the loads and getting them dialed in right. I was told in college, and this was completely wrong, that automotive typically designs to about a 5-to-1 safety factor. Nope. Most of what I worked on in automotive, granted it wasn't safety critical, was we were willing to push it about as low as a 1.2 safety factor. 1.2! And nobody's lives were on the line in that. And we had a pretty damn good understanding of testing and had really rigorous testing with sample sizes of 50 plus parts that would go through extended lifespan testing that was all spec'd out and was industry standard for decades. So we had a problem that we really understood well with lots of institutional knowledge and experience, and we weren't willing to push it any lower than 1.2. OceanGate decided that 1.09 was perfectly adequate. Wow. What in the fucking hell were they thinking? Like, I don't know. It's an unusually cold day and the water is a little bit more dense, and now our submarine is fucking sunk and imploded because, oopsie, we didn't have any safety factor in reserve. Like, this is horrendous. Unexcusably horrendous. And like, whoever signed off on this, my God, this is basically negligence. All right. Now we get to a spicier thing. The real-time monitoring system. You know how I talked about how much I like strain gauges and how cool they are, that you can stick a thing onto, you can stick a strain gauge onto a physical thing and you can measure this curve, and if you've got a good stress or load data to put on it to compare this to for each loading, you can take a look at them and you can compare them and see like, hey, are they all the same? Is it deviating? Is this linear portion becoming, I don't know, non-linear? Hint, hint, foreshadowing. Well, OceanGate Titan was equipped with a system for monitoring the structural health of the pressure vessel in real time. Well, not exactly entirely in real time. They called it a real-time monitoring system. It had 8 acoustic emission sensors and 8 hoop stress strain gauges, or 8 hoop strain gauges. Hoop stress is the stress around like a cylinder, which is important for things that are under pressure, inside or outside. So that's great. And then 8 longitudinal strain gauges. Actually fantastic. Like, this is a lot of monitoring equipment. This is perfect. This is exactly what you need. If you watch these, you can tell. If you watch these, you could tell in real time when you are going from having a nice elastic deformation every single time to when you start to exhibit hysteresis and you start falling onto this side of the curve and going like this. Really helpful piece of equipment to have here. And they're not terribly hard to, they're not really that hard to work with. You know, you need something else to put them against to plot it. Do not plot them against time. Against time is worthless and pointless. You want to put it against load in some way. Some way that your forces on this, like your vertical axis needs to be something that is a relatively constant for the stress or for the strain. So, I don't know, if you're in a submarine and you're going to be experiencing hydrostatic force, which is the force of the water falling, pushing down on you from all directions, or pushing in on you from all directions, rather. I don't know, depth might be a good one, because it's pretty consistent in terms of the load that the water puts on you, because really water temperature doesn't vary, water density doesn't vary all that much when you're diving in the same area. So it would be a pretty darn good tool to plot the stress versus depth, and then keep an eye on it, right? So the acoustic sensors are, some acoustic sensors were co-located with strain gauges and some were not. Whatever. Acoustic sensors and strain gauges were assigned channel numbers 1 through 8, but sensors and gauges with the same channel were not always placed in the same location, so these were placed kind of wherever. This might make sense depending on how their strain gauges were on. Strain gauges, for those of you who don't know, are fairly delicate pieces of equipment, particularly to avoid the strain gauge itself interfering with the test. How a strain gauge works is that it's really just a resistive pad with like a whole bunch of little channels of copper in it. You adhere it to a material you want to measure the strain in. You get a reference point where you say that this is our relative zero strain scenario. So on a submarine, you could zero it out on the surface, and you'd only have the loads of it bearing its own weight on the strain gauges that it's ignoring. And then as the material expands or shrinks, the length of the copper traces are going to expand or lengthen and shorten, changing the resistance, and then a sensor can measure those minute changes in resistance and correlate with that a change in length of the part. So you can real-time monitor strain, which is what you care about for a material's failure criteria. See where I'm getting here? They had stuff to measure everything they needed to know about the integrity of their hull. That's really good. That's pretty cool. I did not expect them to have this. During a dive, acoustic events were continuously monitored via acoustic emission sensors. After amplification of the signal and an blah 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 jargon that we don't really need to know, if an acoustic event exceeded a predetermined threshold, the event was counted as a hit, indicating that microcracking was occurring in the pressure vessel. Pre-programmed levels would trigger a green, yellow, or red indicator to the pilot based on the number of hits. The warning levels were based on the acoustic activity of the V1 pressure vessel. Right here. Based on the acoustic activity of the V1 pressure vessel. Well, when it was tested at the Deep Ocean Test Facility. So there is good and bad here. Let's talk about the good first. So the V1 hull, they had tested the acoustic activity of it and determined what was fine, what was not fine, and used that for its warning system. That's okay, that's good, that's responsible. But this is applied to the second one that they didn't do this for. That's a big red flag. That's a problem. Oh my They didn't do this with the second one, which was constructed completely differently. I'm gonna pull my hair out. According to the third OceanGate director of engineering, if the system detected 30 hits during a dive, the system issued a yellow display warning. If 50 hits were detected, a red warning was issued, and the dive was aborted. Another thing to point out, I don't remember it exactly, but if I am remembering it correctly, the third director of engineering at OceanGate is a software engineer. That's a big red flag. Your guy in charge of what is okay or not on a physical mechanical thing is a software engineer. That's going to be a problem. I know I'm going to go into a bit of a side tangent here. I know people are like, well, you could just learn engineering by going on the job. I have encountered now a couple people who are engineers trained on the job, quote unquote, trained on the job. There are a lot of problems with that. If you're in an industry like automotive or what I'm currently in, you can get by because, well, this is how I've always done it. It's fine. We'll get you through in those two industries. What I have always encountered with these kinds of people is that they don't have the foundational knowledge of engineering. The stuff I'm explaining right here, the stuff that allows me to explain the problems with the design of a submarine that I don't even know how to design, because I can do basic foundational level engineering. Like, this shit is important and people skip over it. Like, okay, the guys I know, props to one of the guys I used to work with on actuators. He knew so much about actuators. He knew so much more about actuators than me. More than I'll probably ever learn unless I get back into actuators. But when I asked him to do a tolerance stack up, he looked at me and he didn't understand the point of a tolerance stack up. Like, it's foundational engineering stuff that people just don't know. And if you're a software engineer, you're probably not going to know this stuff. And this is critical to know when people's lives are at stake. Oh my god, this stuff is infuriating. They processed the acoustic emission and strain gauge data and collected by the RTM system after dives in accordance with their typical procedure. Third and final director of engineering, pressure vessel monitoring data was collected for the V1, but no time or depth information was included. So this is where there's a bit of a problem. Pressure vessel monitoring data were collected for the V1 Titan pressure vessel, but no time or depth information was included. So that's a problem. Only having the strain, I mean, you can do stuff, you can do some things with the strain, but you can't get this information from just the strain unless you have something to put it against. So you need to have like strain versus depth. You got to have that. You can't get away without that properly. During the V2 pressure vessel, the data acquisition software was rewritten to include these parameters and reduce the data to a manageable size. So, okay, then we get time and depth. That's good. You want strain versus depth so that you have basically strain versus stress on your pressure vessel. They plotted for each V2 dive the pressure vessel strain side by side with the dive depth as a function of time. Depending on how you did this could be great or could be really bad. If you've just got like a 2-graph chart, like a two vertical axis plot, that's bad. You want strain versus depth. And then if you're just going to plot that over time, then that's great. But we'll see. OceanGate assumed that as the pressure vessel's condition deteriorated, it would gradually transition from a sound pressure vessel to one that would produce acoustic events of similar amplitude and frequency as the previous Titan pressure vessels. All right, here is another problem. So I would not assume that sound is going to be an indicator. I would assume that if it's making noises, things are bad. I would not assume that it's going to fail loudly with time to act. I would assume that if it's failing loudly, you did not have time to act. I would be focused on these strain versus stress. These are the important ones. These tell you everything. You also can't assume that it would act like the previous pressure vessel that was constructed in a completely different way. That's not how it works. You can't just go, well, you know, I cut this part out of steel and I cut this part out of aluminum, or I cut this part out of cold rolled steel and then this one out of hot rolled steel, so they're gonna fail the same way. No, they're not. They're gonna act different. You need to know how they're gonna act different. You need to test the test that they didn't do on this V2 pressure hull. Cameras, they have a bunch of cameras. Communications, they have some communications. A list of all the expeditions. They had the first pressure vessel that got taken out of action. They'll go over that. We're not going to go over that. The 22 expedition began. They used the same tender as usual during this expedition. Oh yeah, here's another factor. The way that they've been handling the submarine up to now has been they have like a barge that they've pulled onto a tender vessel that the submarine is on. So they load the barge and the submarine onto the tender. They drive it out to the dive spot. They put out the barge with the submarine on it. And then when they want to dive, people get inside the submarine. They flood the barge so that it sinks up to a certain depth so that the submarine can depart from it. And then when they return, it docks with the barge, and the barge has blows out its ballast tanks basically and floats back up. It's actually a pretty clever way of doing it. I mean, it's a really simple way to do it for a submarine, although they've got a submarine that only weighs about 4 tons. I would think a crane would be quite easily adequate for what they need to do on this thing. But that's a clever, cheap way to do it. I'm not going to dock them from that, although their methodology did have some problems as they've seen a lot of trouble with their barge throughout this, but I'm not going to really go into that. They experienced a bunch of problems with the submarine during 2022. On July 15th, 2022, Mission 3, Dive 80. So this is Dive 80. The casualty dive was Dive 88. So we're getting close to the casualty dive now. And we're with the same pressure vessel that was the casualty dive pressure vessel. So people inside the Titan and the crew of a small boat on the surface heard a loud bang as the Titan ascended after successfully reaching the Titanic wreckage 3840 meters. According to a former missions specialist, they were told the hull had shifted in its metal cradle. That's a cause for concern. If anything is shifting, that's a big concern. CEO wanted to continue operations, and after inspecting the strain and acoustic emission data, told the director of engineering, "Let's dive again and see what happens." Let's see. Do they say anything about how many people were on board? Like, was it people or like no one or what? I don't think that's explained, but like if he wanted to take it out and see what's going on, okay, that's fine. You know, risk your own life, see what happens. That's okay-ish. But also you should analyze your data and see what your data says, which supposedly they did. Titan completed 3 additional dives following Dive 80. Mission 4, dives 81 through 83. The submersible reached 3,800 meters. on dives 81, 82, and 2,900 meters on the final dive of the expedition. After the 2022 expedition, the Titan was initially stowed at an outdoor facility in John Hall. That's in St. John's. It was left in a parking lot. So they, between seasons in the winter, they just left the submarine outside uncovered, middle of winter. Oh, fucking God, why? Dear God, please. Our extremely delicate thing, made out of carbon fiber, known for deteriorating when left to the weather, we decided to leave it to the weather. Oh my God. You couldn't rent like a fucking storage unit to shove this thing in? Like, please, for the love of God. Oh my Jesus Christ, people. 2023 expedition, they charted Polar Prince. So this is a different tender. Instead of what they were doing before, what I mentioned, where the submarine was on the barge, and then the barge was loaded onto their tender vessel, during this expedition, the Titan and its barge were just towed behind their tender. So now you have the barge facing open sea waves with the submarine on it, just bouncing up and down all over the place. Who thought this was a good idea? Like, please. Oh my, there's so many things that have gone wrong at this point. And they just towed it, and they're like, yeah, this is fine. It could go wrong. Mission 1, they didn't have anyone on board. Mission 2, one uncrewed dive for a system check on dive 84. Dive 85, along with 86, were unsuccessful, and they didn't go down to the Titanic wreckage. During dive 87, the dive was aborted due to ballast issues and a malfunction with the Lars. So, basically, since the dive where they heard the loud bang, I think there was... Where's the table of it? Which one was it? Dive 80? So dive 80, they went down to... Okay, so after dive 80, they went down to their max depth twice. They didn't go all the way down once. And then they did a set of shallow dives. So that's 3 cycles before failure after that loud bang. That's what you would expect when you have catastrophic damage. I'm surprised it lasted 3 times. On missions 2 through 4, Titan was not able to launch due to weather, blah, 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 blah. So here's some pictures of how they were towing this submarine. It's just on a relatively small barge on open ocean. If you know boats, if you've been on a boat, you know that this is going to be pretty darn rough. I have a small speedboat that my friend takes out. We only go out onto interior lakes. They're some pretty big interior lakes. They're not the Great Lakes. They're still pretty big lakes. And when he gets going at like a decent clip, and it's a little bit windy out, it's pretty jarring. You're getting like bounced up and down. You're smashing into the waves. It's pretty rough when you're on a small boat. That's what's happening to this thing when they're towing it out there. That's not great. The damage to the thing. Okay, so they did end up recovering. They recovered some of the stuff, and here's the forward dome. There's the aft dome. This is the wreckage of the thing. Where's the thing where they're going to talk about it? Wreckage examination. The NTSB examined a piece of the V2 composite cylinder, which had been recovered from about 350 feet from the main wreckage and measured about 61 inches long by 20 inches wide by 1 inch thick. Oh, so 1 inch thick, it's exactly one ply. One full layer of their pressure vessel. Which, hey, it's a little weird that their pressure vessel imploded and it separated into plies. Like, it might say something, like what I've been talking about before of how the way that they constructed their thing is really shit and is a problem. Maybe not really shit, but like you got to control it really carefully, otherwise this will happen. The outer surface revealed it was coated by a green film adhesive, and the inner surface was white paint. So this is the first layer interior of their pressure vessel. One end of the piece was machined, and some bits of cured adhesive were still attached. The other edges were fractured. So this is towards either the fore or aft side of the thing. We also examined the end pieces that had been trimmed from the V2 full-scale cylinder. So these are the big chunks at the fore and aft end of the cylinder that were cut off. They had wrapped up more than was needed. That's, as far as I've seen with carbon fiber, that's pretty typical. Our examination determined that there was porosity between the plies, voids in the adhesive used to join the co-bonded layers, and pre-existing disbondment between the first and second co-bonded layers. It's almost like building your thing in separate layers means that you have to have a really good process to bond them together, and they didn't. My God, why? Like, this should be stupid obvious to anybody with an engineering degree. This is like up there in me pulling my hair out with the Ordnance Department's Mark 14 torpedo, and they just go, let's move this pressure sensor to a point where the pressure is just going to inherently be lower because of fluid dynamics. Like, no, you guys fucking know fluid dynamics. You know you can't do this. If you know anything about materials, you know you can't do this, guys. Wrinkles and waviness in the carbon fiber were observed on the trimmed end pieces, and multiple wrinkles in the carbon fiber had been leveled flush with the outer surface using a grinding tool during the manufacturing process. So, even better, we've got a material that relies on the strength of fibers being wound around it, and we decide that we could just cut some of those. That's fine, right? What could go wrong if we, remove the one strength feature of carbon fiber in our design? Oh my God, why, people? Then here's an example of cross section of layers 1 and 2, showing the adhesive between the layers and the voids in the adhesive between the layers. Oh my God, this is horrendous. Look at all of these voids. Like, they didn't even glue this thing very well. I don't know what to say. This is fucking horrendous. If you don't have these perfectly adhered, or at least adhered well enough that they don't move relative to each other, they're gonna start moving relative to each other, and they're gonna start scraping across each other, and they're gonna start weakening each other. Which as the NTSB found, the adhesive regions were rubbed flat, and adhesive wear debris was found collecting in the voids. Yep. Cracks in the adhesive and the carbon fiber were consistent with shear sliding between the already separated first and second layers during the implosion. Yep. They examined the end pieces of the original, and you see the original had some pretty bad delamination as well, and some pretty bad wrinkles. At least this is their first full-scale pressure vessel. So yeah, that's really, really bad. You want your material to be homogeneous. Anything that breaks up the continuity of your material is going to be stress concentrations. All right, let's get to... Wait, did I skip it? They had graphs for the real-time monitoring system. I hope I didn't skip over. Or maybe that's later. That must be later. Scrolling. They talk about, okay, acoustic emission and strain gauge data from the dives. So they've got some data from some of the dives. They don't have complete dive data, but they've got complete data available for dives 75, 76, 79 through 83. And OceanGate plotted dive data from the 2022 expedition dives against time and correlated it with the vessel's ocean depth. So it sounds to me like they didn't just have a good plot of strain or acoustic events versus depth. They only had it versus time. And then they'd have to take a look at what was going on for each time and depth. No data was available for the 2023 expedition, including the casualty dive, because the implosion destroyed the storage dive, and none of the data was recoverable. They reviewed the data, prepared, and they ended up, well, I'll give you the short of it. They ended up preparing these graphs of where you get the green line is the depth of the submarine. You've got time on the bottom axis, then you have amplitude of acoustic events, purple, left axis, and depth is the right axis. So you see dive 80, the one where they heard the bang, you see this huge spike of acoustic energy, and it's not a one-off. There's additional ones that come around it, and then sporadic ones, but I can't really draw any conclusions about these additional ones or the rest of the data outside of this one without having some contextual data. Then we have strain gauge data, which, you know, like you get a pretty significant anomaly. That's pretty not good. But from this alone, I can't really tell you what that means, because it's a jump in data. It could be erroneous strain gauges. It could be, you know, like a computer failure, or it could be the strain gauges have slipped in their mountings. Although it depends on if they all did that or not. But it looks like a lot of them did. All right. Now, here's what I'm looking for. Let me zoom in on this a bit. Okay, these are both, you guys have a little bit of cutoff here, but these both have exactly the same scales for on the left side. So these are strain gauge output versus ocean depth. What does this mean? Well, strain gauge output, so it's just a value. But if you correlate that with depth, it's good enough. It'd be nicer to have the strain percentage, the strain units, because if you have strain units, you can tell by the data, like, hey, we're exceeding our reasonable strain values. But raw output is good enough for what we need. And we see that dive 75, dive 80, you know, we're getting dive 75, we get descending. It's a pretty good linear descent, and then and then coming back on the ascent, it's pretty linear. I mean, it's messy data because it's raw data, but it's linear. It's a goddamn straight line. Like, this is really good, really good. Like, the pressure hull's performing pretty good on dive 75. Dive 80, it looks a bit messier, and then we get the ascending, and they're at 350 meters here, and there's a burst, and what's this? More than 500 meters, so that doesn't quite correlate, but That's nearly... Wait, no, they're pretty low. They're on the surface here, it looks like, with this strain gauge. This might be potentially an error in the graphs. I don't know. But you get... It looks a lot more messy here. There's a couple small... I mean, I would probably discount some of this small bursts, but this right here is concerning data. Like, what's going on with this? That alone, you can't really make any judgment calls. I would probably say if all of the other data looks like dive 75, but then dive 80 looks like this, I would say, can we do like an unmanned dive and just like lower the thing down to a good depth and see what the strain gauges are looking like? And then we get dive 81, 82, and 83. Hey, this isn't linear. Remember how I talked about hysteresis? Where you're normally coming up straight and you're coming back down straight. And eventually you're going to come up straight and you're going to come back down at an angle and you're going to start going up at at a curve and you're going to come down at a curve. Their data picked that up. It's right here in front of us. They had enough monitoring to see that their pressure vessel is compromised right here. This is beautiful data. This is fantastic. You could have gotten to dive 80 and you could have seen this data and go, I'm not sure what's going on. And then you could have done dive 81 unmanned or one person. You could have done one person even in this. Gotten this data back, took a look at it and went, yeah, chief, that ain't right. This thing ain't safe. And called it quits right there. This is like irrefutable. Like if I had seen this just on its own, I wouldn't have thought much of it, because typically we don't get super perfectly linear data in strain versus stress. Like it's not as clean as what I drew here, like in anything that I've seen in my experience. But they had that. It's perfect data. And then they get perfect data saying that their pressure hull is not working. And they ignored it. They missed it. I don't know what happened there. But this is awful. This is horrifying. Like all of the data is screaming at them right in the face. This is not okay. And they've got an entire system built for it, and they just didn't. Like, God, I don't know what else to say. It's just so bad. So then that's kind of the end of it, of the technical discussion we can have here. Does anyone have any questions before we go on to just looking at like the NTSB kind of conclusions? Or I mean, they're not kind of conclusions, they are conclusions. All right, so the main takeaways that the NTSB has had with this, they've got takeaways. If you're gonna read this, I highly recommend you read the analysis section here, or the conclusions. We can skip to the conclusions. Sounds like a mixture of poor design, terrible management, and extreme negligence. Yeah, I think that this is negligence. No ways about it. Like they didn't test to failure their they didn't, like, even scale model testing. I would accept scale model testing as due diligence. They didn't do scale model testing to failure of their design to know their actual safety factor. They looked at their test data of a 1.09 safety factor and said, this is fine on a material that can't have indefinite lifespan, which for me is just baffling. Like, oh my God, you need a good safety factor for that. I would, with a submersible, I would have probably gone with a 3 safety factor. Yeah, that's more weight, but weight isn't a huge problem when you're a submarine that wants to sink. But conclusions and then the real-time monitoring system, they had everything they needed to put a stop to this before anything bad happened, before the pressure vessel was compromised. We saw the gradual failure of this thing. Like, it was it was a pretty quick failure, but it was not a failure that happened from everything's fine and dandy to the submarine has imploded within one dive. It was multiple dives. So they had the capability to see the failure, and they just the why they didn't see it, I kind of wish there was more information on. Like, was it they couldn't read that data and put it together, or they read that data and they saw the curve and they didn't think anything of it? I think it's probably more the latter, because if you don't know what I've explained to you here, that data doesn't really, like, okay, it's a little bit of a curve, but the absolute value of these values is still relatively the same. So it seems like we're fine, right? No, you're not fine. You need an engineer or someone with a technical background in this to talk to you about that. Like, I mean, you guys now know enough about this because I've explained this. That's important. The foundational engineering is important. All right. Conclusions. I am probably gonna just read through all of the conclusions of this, because this is the end of the report. The conclusions and the recommendations, because as awful as this incident has been, there are some good findings there are some fantastic findings the NTSB has found. I adore the NTSB for their thorough, God, I'm trying to put this in words. Their methodical nature and thoroughness in these reports, in that there's never an NTSB report that I've read where it's just like, yeah, this happened. What recommendations do we have? It was a fluke. It's never that. They always have recommendations, even whether they're perfectly reasonable or if, like, they're just, these are things we can't do yet. They always have recommendations, and typically they're pretty damn sound recommendations. And the conclusions and recommendations will go into some stuff that we've skipped, but I'll mention it as we read through. The Titan pressure vessel likely sustained damage after it surfaced at the end of Dive 80, in the form of one or more delaminations that formed from voids between the cylinder's 5 co-bonded layers, leading to the deterioration and weakening of the pressure vessel. After Dive 82, the Titan sustained additional damage of unknown origin that could further deteriorated and weakened the pressure vessel to a point where it could not survive a depth to the Titanic. The existing delaminations and additional damage that deteriorated the condition of the pressure vessel between Dive 82 and the casualty dive likely resulted in a local buckling failure that led to the implosion of the Titan. OceanGate's engineering process for the Titan was inadequate and resulted in the construction of a carbon fiber composite pressure vessel that contained multiple anomalies and failed to meet necessary strength and durability requirements. Because OceanGate did not perform adequate testing, including life cycle evaluation of the Titan pressure vessel, the company was unaware of its actual strength and durability, which was likely much lower than their target, as well as the implications of how certain operational changes, including storage condition and towing, could impact the integrity of the pressure vessel and overall safety of the vessel. Because OceanGate's analysis of Titan pressure vessel strain gauge and acoustic emission data was flawed, the company was unable to identify that the pressure vessel was damaged after Dive 80 and that it needed to be immediately removed from service. Had OceanGate followed Navigation and Vessel Inspection Circular 0593 Guidance for Emergency Response Plans, they likely would have had emergency response assets standing by, and the Titan would have likely been found. Titan likely would have been found sooner, saving time and resources, even though a rescue is not possible in this case. So the Coast Guard, in a lot of this part, in a fair amount of this, the NTSB goes into how the Coast Guard was able to within about 5 days, I think it was, get another submersible capable of diving to the depth of the Titan to go start looking for it. So the Titan, with its air reserve of 4 days, literally did not have enough. It didn't have enough air for the people to survive in it should it have a malfunction at depth. This thing didn't have any safety factors. It didn't have any plan Bs. If the submarine had just went kaput and dropped as a completely intact pressure vessel at the bottom of the ocean next to the Titanic, there was no option for rescuing them. They would have suffocated before anybody came to rescue them. Despite OceanGate's, they also waited way too long to notify anybody that they needed help. That's going to come up in this next point. Despite OceanGate's failure to notify search and rescue assets about its planned expedition and the limited resources available to operate at the depth of the Titanic wreckage, the U.S. Coast Guard's response coordination efforts were effective and resulted in a timely discovery of the Titan wreckage. Voluntary guidance and current U.S. small passenger vessel regulations are not sufficiently tailored for current pressure vessel for human occupancy operations to ensure the safety of pressure vessels for human occupancy in accordance with established technical and classification society standards. NTSB, please use more commas. Oh, oh my god, that is a lungful right there. Internal standards for pressure vessels for human occupancy would ensure consistency in design, construction, and operation requirements for pressure vessels for human occupancy that operate around the world. So another part of this is that there aren't really many standards for the submersible. They went into in this a bit about the CEO not wanting to bother getting their submersible classed because, well, what's the point? It won't ensure safety. He probably didn't want to get it classed because all the classification societies said, yeah, no, we're not going to class this piece of shit. Get the fuck out of here. But that's my opinion. Another thing that they brought up with this is that the passengers on Titan were not passengers, they were mission specialists. They weren't passengers, they were crew, technically. Which meant that this wasn't a passenger or a tourist submarine. This was a scientific vessel, which means that it circumvents some legislation, which is what they went into talking about way up here. So back in the 1960s through 1993, a fair number of submersibles were made that were passenger or tourist submersible. However, everybody in the industry realized that they could just say that their paying passengers are actually crew and not be passenger or tourist submarines. And they'd just be classed as other submersibles as long as they have a small enough passenger count and gross tonnage. And that's going to come up in a little bit with the recommendations. Probable cause. The National Transportation Safety Board determines that the probable cause of the hull failure of the implosion of the submersible Titan was OceanGate's inadequate engineering process, which failed to establish the actual strength and durability of the Titan pressure vessel and resulted in the company operating a carbon fiber composite vessel that sustained delamination damage that was subsequently exacerbated by additional damage of unknown origin, resulting in a damaged internal structure that subsequently led to a local buckling failure of the pressure vessel. That's a lot of technical, but yeah, it just suffered damage and it broke over a couple more dives due to fatigue failure. Contributing were U.S. and international voluntary guidance and U.S. small passenger vessel regulations that were insufficient to ensure OceanGate adhered to established industry standards. Also contributing was OceanGate's flawed analysis of their pressure vessel monitoring system data, which led to their continued operation of a damaged pressure vessel. Again, as I mentioned, that data we saw where it goes from a perfectly straight line to a curve is horrifying to me. I look at that and I go, oh my God, something is wrong here. Now, granted, when I looked at it the first time, I looked at the data and I went, okay, well, it went from linear to curve, and I had to look at the data for a minute, and I had to think a little bit about this and remember hysteresis. And as soon as I remembered hysteresis, it clicked and I went, ah, oh my God. Part 4, recommendations. As a result of this investigation, the NTSB makes the following new safety recommendations. The U.S. Coast Guard commissioned a panel of experts to study current pressure vessel for human occupancy operations, including at a minimum the ability of domestic and international design and construction standards, competency between credentialing persons on board, the distinction between crew and passengers, and whether all PVHOs should be inspected regardless of operational category, maintenance and operation of submersibles, the effects of operational changes such as storage conditions and towing, failure modes and best practices, the emergency response procedures, and disseminate findings of the study to industry. I need a drink after all this. Drink of water, to be clear. There's a lot of talking in this. Implement U.S. regulations for pressure vessels of human occupancy, informed by the findings of the study recommended in safety recommendation such and such. If necessary, obtain legislative authority to act on this recommendation. Revised navigation and vessel inspection circular 0593 to include the revised definition of small passenger vessels as reflected in the Passenger Vessel Safety Act of 1993, and to reflect the findings of the study recommended in this numerical recommendation. Propose that Internal Maritime Organization make this circulation mandatory to promote consistent application of pressure vessel for human occupancy rules against member states. So, out of all of this, what really comes out is that these submarines are basically unregulated because of a loophole. And so the NTSB has great recommendations about trying to get these loopholes patched so that way these submarines can't be uninspected. They have to be inspected, they have to be certified. That's a good takeaway. So out of everything with this, some good has come. The real question is going to be, is anybody actually going to get in trouble for all this shit? Which I hope so. Someone gets in trouble for all this shit. All right. Well, I guess that's about all I've got for this. We've covered everything that I wanted to cover. A little bit more. It looks like we will be doing some stuff. I will likely be back later in a couple hours. I just need a break and maybe some food. And then we will be playing, Derail Valley, I think. We gotta fix the trains that we absolutely wrecked. Let's find someone to raid into. Who is online? Why do I not have Twitch up? You are free? How are you free? Upgrades are complete. You know, we were talking about ocean-related stuff, and Illith is online, so let's go raid Illith. Alright, make sure you give Illith a nice raid 1. I will be back 2:30. Let's go with by 4:30, probably. play some Derail Valley, me cursing and swearing at the poor decisions of past Mika. It'll be a fantastic time. I'm probably gonna get a couple drinks after reading through that stupid NTSB or that really good NTSB report about a whole bunch of stupid people. Oh my god. Anyways, I'll catch you all later. Bye-bye.